So a few of my team members over the weekend have been cooking a really good model, and we released last Saturday, or this Saturday actually. And so if you haven't tried it, you can open your ChatGPT app, and if you don't have it, please download it. And if you click this, it's hard to discover, but if you click the button there, there is a, so you will enter into the video speech-to-speech model. And for example, we can try. They're on the far right. Yeah, it's really hard to discover. I'm sorry about that. And hey, I'm actually giving a talk right now at Columbia about AI. Can you make a joke about Columbia, which is appropriate?
A light one for you. Did the AI apply for Columbia? Because it heard even the algorithms get a degree of sophistication there. Good luck with your talk.
Okay, that's not bad. Okay, cool. Now let's skip the ad and let's start the talk. So it all started around 1948, 1950. Turing asked the question, can machine think, right? And so this will come back again and again. When people talking about can machine think, I really like the framing is, we're not trying to simulate an adult brain. We're actually trying to simulate an infant's brain and then subject to an appropriate course of education. So that's exactly what machine learning is. And we will come back to this as well. And then today, in the history, I will tell about the history of two deities. One is self-supervised learning, and the other reinforcement learning. So let's go to the self-supervised learning first. About 13 years ago, there's the AlexNet. So basically, that's a first large-scale deep learning model, like use GPUs and a lot of data that basically achieve astonishing error rate on ImageNet, much better than before. And one insight we got from this is, with sufficient data and compute, and neural network surpass humans, hand-engineered vision algorithms for the past few decades. So this is kind of, back then, for the people who work on vision, like with the hand-tuned features, it's a disaster. It's a nightmare, because all their work for the past few decades doesn't worth anything anymore, suddenly. And so this actually revived the interest in neural networks, and deep learning revolution began that year. Most people see that's the year marked the deep learning revolution. And then 2013, there's a really fun finding from Google, word2vec. So basically, you can use a vector, embedded vector, to represent words. And you can do arithmetic on those words, like king minus man equals to queen minus woman. So you can have semantic meanings in the algebra operations. And the other thing is actually, then if you use the embeddings, they're really good in the downstream tasks. So this kicks off another two trends, right? One is from word2vec to everything to vec. Everyone wants the representation of the entity. You can represent the app when you're recommending apps. You can represent the video when you try to recommend videos to users and so on. And the other thing is reinforce compute plus data is much better, performs much better than inductive bias. Like if you go back to Turing, right? Turing said, we do not want to simulate an adult's brain, meaning we do not want our human inductive bias in the models. We want the model to be minimum structure as possible. And you want to build a model that just want to learn, rather than we build a lot of human priors in that. And this, again, proved that compute plus data is much better, better than several decades of human engineers. And 2014, there's a really good paper called Generative Adversarial Nice. So basically, you have two nice. One is a generator, the other is discriminator. This has not a lot to do with self-supervised learning, but it's a really great idea that applied almost everywhere later. Let me skip that. 15, there's a really good method for optimization called ADAM. And this really accelerated the progress in deep learning. The reason is, you have a standard way of learning algorithm. You don't have to hand-tune a lot of the parameters anymore, and it's really good for large data set, especially for noises, sparse gradient. So they streamlined a lot of the training frameworks. And so even until now, I think a lot of optimization methods are just variations of ADAM. They're not the plain of ADAM learning, but it's very close. And 2015, another really good paper coming out, ResNet. So this is a really good paper. Basically, the problem we were facing is training very deep networks were really, really hard because you have a very deep network, the gradient vanish or explode, right? And the genius idea is ResNet implies this basically skip connection. Like every layer can skip to the next layer as a raw input. So you don't have to. It's basically, you can think of this as an ensemble method. They ensembled every layer of the model from shallow to really deep networks. So that this is a really good illustration. If you look at the area surface, and A is the one that you don't have the residual connections, and C is very spiky. Those things are very hard to optimize, right? And for B, it's a very smooth like loss curve, so you can easily optimize that. It's much smoother. So basically, this is almost all the modern network. If you employ such a structure to make sure it's much easier to learn. This is another fundamental paper that came out. And then back then, there are a lot of fuss about deep learning. Like people has a lot of doubt, and including myself. I started with a pure math background. I think there's a lot of things is intuitively is not correct, right? I was talking to a statistics professor yesterday. Actually, I realized a lot of things I learned in graduate school about statistics, the intuition are wrong. And the reason is, before people live in such a lower dimension space, the intuition we get there do not generalize well in the higher dimensional space when you have a trillion parameters. And so I urge everyone in statistics, we should just study more of those problems rather than the traditional problem, because the intuition we give to students might be wrong. And I had to spend years to overcome those, wrong intuitions. So one of them is, deep neural nets. This is a non-convex optimization. When you work on non-convex optimization, the first thing you worry is they will stuck in a random local minimum, right? Depending where you start, and that's really bad because how do you trust the result if the best solution going to stuck in a random local minimum? And then there are a lot of studies on this. I think the thing make me feel confident is, one, in a really high dimensional space, it's actually really hard to stuck at a local minimum, because we live in the 3D space, right? And when we see the 2D surface, right? There are a lot of local minimums, and they're really bad. But it's really hard to escape because you only have 2 degrees of freedom to do that. But when you live in a billion or trillion dimensional space, it's really hard to stuck in a local minimum because you have so many degrees of freedom. And the other thing people find out is, even in that case, you stuck in a local minimum. The local minimum first is not really bad. It's actually a really flat local minimum. It's actually a good one. It's not very far away from the global minimum when you plot the data, the loss surface. And so those kind of two things, I think, make sure people don't worry too much about the local minimum, non-convex computation anymore. And again, our intuition is 3D work give us a lot of fat, but those things does not hold in the high dimensional space. A similar one is, if you're on a plane, the probability of random 2 vectors are orthogonal is almost 0, right? But if you look at in n-dimensional space, the probability that random 2 vectors are near orthogonal is almost 1. They're almost orthogonal, almost. And those are different intuitions when you have a low versus high dimensional space. Am I going too fast or too technical, or this is okay? Good? Okay. A little bit too fast? Okay, I will slow down. Yeah. Fact number 2. And so if you're from traditional statistical analysis, right, you have number of parameters larger than the number of data points you have. That's a disaster. That leads to overfit, theoretically, right? And so that's another fact, because in most deep learning models, the number of parameters are usually, you have more parameters than data points. And why doesn't lead to overfitting? That's another fact people, because I train as a math major and statistics major, so that's also always give me a fact. And then there are a series of studies. The good ones are, I think, one thing that convinced me is, even though when you have more parameters than data points, you can fit to random labels, right? You can fit to random noise. But what we discover is the deep learning model always learns the pattern first. Because we will come back to this. When the stochastic gradient descents learn, they will learn the feature space where they have the largest eigenvalues. And that basically means where you have the most pattern, they will learn that first before they learn the noise. So that basically means even though you're over-parameterized, it doesn't matter, they will learn the pattern. And what are the other good things? Then there's also this double descent paper that similar idea, right? When you have really over-parameterized model, once the network can interpolate, then it's entering into a world, there are a big surface of zero loss points. And then the model tends to pick the best one. So that's overcame, but at least for myself, that overcame that, this is okay. Over-parameterization is actually a good thing rather than a bad thing. So then there's the sequence-to-sequence model learning and attention. So 2014, there's from Ilya sequence-to-sequence model. This is used everywhere in all the applications and in the machine translations. And then 2014, there is attention. That's the first attention paper. That's not the attention is on need, but it's attention on some other architectures. And the major challenge point back then from 2014 to 2016 is those recurrent models are really to train in parallel because it's recurrent structure, right? You have to train the first step and then the next step and so on. And basically that limits the size of the model and also the size of the training data when you cannot parallel stuff. And the other thing is RN suffer from gradient vanishing and on the time horizon. I mean, we solved this depth dimension, the residual network can help the gradient vanishing, right? But on the time horizon, still suffered. LSTM helped, but still didn't solve the problem completely. And then that's where transformer came in. This is the most important paper almost in the last decade. Not a lot of new things. They're basically combining a lot of things that we talked about already, but this is the architecture that solved most of the concerns we had before. And it's basically eliminated the recurrence entirely and rely solely on self-attention. And transformers, basically stack the multi-head attention and feed-forward layers. The advantage is there are much better data efficiency, and it's also much better parallelizable compared to before. So you can train much larger models with much more data. And this has become the backbone for nearly all the cutting-edge NLP models and all the multimodals also. And then something really interesting happened from there. So there's 2018, there's the GPT-1. 2019, there's GPT-2. 2020, there's GPT-3. And we discovered those models are really generalizable. I think people call this area generative AI. There's another Gen AI. I personally prefer Gen stands for generalizable. I think that's more the essence of this. Before we can build models for anything almost if you have data, right? But the thing is, you need to build a specialized model for any domain you want, and that's not scale. And this regime of models, they're actually super generalizable. You can zero shot or few shot to make it do your task. So that's make the intelligence per the cost per model lowered significantly. And then 2020, there's a really famous paper on the scaling law. So basically, the x-axis is the loss, the lower the better, and the y-axis is the compute on the log scale. So you can see there's a really clear log linear plot on compute, on data size, and number of parameters. The more compute you have, the more data you have, the more parameters you have, you actually have a lower loss. This is the really beautiful curve, like in case you haven't seen that before. It's going to plateau at some point, depending on the data. But this is not the physics law. It will probably not hold at some range, but we will see. So when we apply that scaling law and trying to predict GPT-4 before GPT-4 even born, it's almost predict perfectly of the GPT-4 performance. And basically, this means the scaling law holds across about 13 order of magnitude. And that's a lot. That's 10 trillion, right? And then let's go back to the point we started in the beginning. This is the beta lesson. If you haven't read it, I strongly recommend you read it a few times. I've been reading this like maybe 10 times over the past few years. And every time I read it, I get something new. So this is a really good material. So So basically, the bitter lesson over the last 70 years, remember the AI started 1950, is, we want minimal inductive bias. We want the method that scales with compute. And the two methods that scale with compute, one is search, the other is learning. Search here doesn't mean Google search. It means you explore new ideas and so on, right? And for example, in Go, you explore different moves. And so the gist of that is basically compute ultimately outperform, the algorithm that leverages compute ultimately outperform those relying heavily on human engineered inductive biases. We see that on image, we see that on NLP, we see that on everything basically. If you have data and compute, you want to build a model that just learns rather than you want to human engineer a lot of human inductive bias into the model. If you don't take anything else from the talk, that's the thing I want people to take out. Then there are a lot of, as a math major, that makes you wonder again is where is scaling coming from? It's just observation, right? And people's nature is we want to understand where it's coming from. There are a lot of hypotheses. The major ones that register with me is one is scaling law actually reflects the structure of the data distribution. If you look at the data, the data distribution follows a power law. And so, for example, a really good doctor can solve rare diseases, right? And a mediocre doctor can solve the common diseases. And similarly, the higher the intelligence of the data is actually occurs less often. There may be millions of books on arithmetics, but maybe there are a few on algebraic geometry, right? So that power law distribution is kind of what maybe underlying the scaling law. Like you need extra 10x more compute to discover the things that's more rare in the data or higher intelligence in the data. And so this basically suggests the scaling law is actually not from anything else, but it's actually from the data's intrinsic property. So that I really like the interpretation. We will come back to that. And we'll also talk about how a model learns the most common patterns first, right? And it's similar to when you do a principal component analysis, you do an eigenvector decomposition, right? They will learn the eigen features with the largest eigenvalue. And that's the nature of the SDG. So SGD is a natural compressor. The other thing that people always wondered, maybe 2-3 years ago, there are a lot of debates on the internet or Twitter, is why those emergent abilities happen. You see the eval here, right? They don't go smoothly for like math capability. It's just suddenly the model can solve some math problems, right? And why is that? And I think this also roots back to the scaling law, is even though the perplexity, the loss is actually smooth, but because of the power law in the data, the capability suddenly came, right? Because when you have 10x the compute, you finally understand calculus and then can do calculus. And so it always depends on how you measure, because you can always, convert a discrete variable to a continuous variable in some way. But I think it's just how we view it. But so that's why people call that emergent abilities. I don't think people should be surprised by that. It's not suddenly. It's actually just what reflects in underlying data. So this is Ilya, and one famous saying he has: the models just want to learn. I think at that stage, and we actually have a decent model architecture with this transformer that the model just want to learn. You just want to feed the model data, and that's actually a really good thing to have. So, okay, so we overcome a lot of FUD for the last 10 years. And this is another one. I think a lot of people, including myself, do not have a lot of conviction. Now I do. But the thing is, does compression or prediction lead to really understanding and intelligence? And we don't know, right? But there are two perspectives. One is from the information theoretical perspective, is Shannon defines information as unpredictability. So if you can completely predict something, there's no new information to you, right? And so intelligence can be seen as ability to reduce surprise. Like if you are not surprised by anything in the world, which is hard, that means you're really a wise person in many ways, right? And so if you think about what LLM does, LLM basically, by predicting the next word, they are basically compressing a lot of the patterns so that it wants to get less surprise over time. And so in that way, you can understanding basically predicting the next word or compressing the patterns is kind of a form of intelligence, similar to how human predict the world. The other thing is from cognitive science perspective. Like as human beings, we have been trying to compress the infinite amount of information in the universe into physics laws, right? And Newton has the law of motion. We want the unified field theory. Those are all compressions. We have a lot of observations, and we want to compress them into minimal set of laws as possible. It's similar for math. We want the axiom system, right? And the other thing is our brain constantly compress sensory input. So if you look, like if you're looking at something, right? If something surprise came in, you will have reaction to that. Otherwise, you will not. So your brain actually have a good way of compressing things that don't surprise you, but digesting only the new incremental information. And in that sense, learning is compression. Like when you learn a new theory, it makes you excited and curious, and then you learn. But if you reading something boring, your brain already compressed that, you get bored in many ways. Cool. Those two things is, to me, they're really good explanation why compression just at least implies a large portion of intelligence, maybe not all. Okay, so that's the first city, which is self-supervised learning, right? And let's go to the second, the reinforcement learning part. The whole thing, the deep reinforcement learning started in 2015. There's a DQN, the DeepQ network, that can play, 2,000 Atari games really, really well, much better than human. I don't know if I ever watched this video. Some of them are super fun because I'm growing up playing Atari games, and they discovered a lot of strategies I never imagined. It's just, people call that alien intelligence because they're not, the way they learn is they play and they reinforce, right? But they don't necessarily copy from humans. So they invented all those things that humans never thought of. And similar for AlphaGo. And 2016, I think that's the biggest event maybe in the last decade about AI. People got really excited because Go is kind of the moment people think, oh, there's really a lot of intelligence in these models. The AlphaGo actually bootstrapped it from the human games, and they basically combined the deep neural nets with self-play and Monte Carlo tree search. They defeated the world champion. And 2017, they refined that to AlphaGo 0. So basically, they didn't bootstrap the deep neural network with any human data. It's all from self-play, and which is just amazing. And this is actually very interesting. I also read a lot of, I don't know if like Kung Fu writings, and there when I was growing up, I read a lot of this. There's actually a Kung Fu master who are doing that. He's so good, he cannot find anything that defeat him. He started self-play. Like he will just fight with the left and right arms and so on. It's very similar to that. And you basically you split your brains and your body, and then you fight each other. It's pretty fun. Then 2018, there's Alpha 0. Basically, you can just, with minimal human inductive bias, you just tell the model that the rules of the game and what is a win and what is loss, and no human data at all, no domain-specific tricks, and they can play chess and shochi really, really well, not only Go. And then 2019, people moved to like the digital video games, like a StarCraft, and become the grandmaster there. And then the interest along those lines died down because we actually proved we can play any game really, really well. And we will come to a question why it has less impact. Then there's another branch, is Berkeley and OpenAI, folks, group of people. There's a TRPO from John Schulman, and they address the instability of the DQN. And then there's a PPO who is behind the ChatGPT algorithm, which is simpler to implement, it's more general, and has better sample efficiency. And then there's OpenAI also has OpenAI 5. Rather than the StarCraft, they played the Dota 2 and become the world champion at Dota 2. And the question is, though, why did this impressive RL achievement have limited direct impact on productivity and everyday life? Like they generate a lot of hype, right? That people, the model can play Go and so on, but they generate like minimal economic value. And the reason for that is, they don't have economically valuable generalizable prayers and environment. They're very specialized. It's specialized AI or specialized superintelligence in some way. And then things changed when we combine pre-trained RL. So I call this a paradigm one of pre-trained and low computer RL. So basically 2022, there's InstructGPT, basically training language model following instructions to be useful, right? If you don't fine-tune the pre-trained language model, it's just it's an auto-completer. It doesn't really do the things that you want the model to do. And 2020, there's ChatGPT. So basically with similar method and using RLHF, there is actually a very low-key research preview by John Schulman, Barrett, Luke, Liam, and people said, oh, let's just put it out there and see how people use it. And now there are way over 500 million users use ChatGPT every week. And I'm always every day amazed by how helpful this ChatGPT can be. This can save people, literally save people's lives. There are users who are uploading their years of medical history and find out things that the doctor never told them before and save their lives. This is the reality. And I use ChatGPT every day. And not only the voice mode, I use deep research every week. And I think my search volume went up like maybe 10x because I'm using deep research. The model is doing all the searches for me. I don't have to do that myself. And it's like even better than a intern in many ways. No, sorry if you're. Yeah. So, but then you think about this, what changed from the game RL, right? Because we mentioned the game RL is not that useful. And I mean, that's an understatement. It's really useful, but they didn't generate a lot of economic value, but now it does, right? And so the reason is now RL is combined with a much more generalizable prayer, which is a pre-trained LLM. And and also apply to environments that can have a lot of economic value. But then you ask yourself, where is the generalizability coming from, right? The majority of the generalizability still coming from the pre-train. Why is that? The pre-train is basically the next word prediction. And this thing has almost minimal inductive bias. Like Ilya said, the model just want to learn. It's just a simple loss, and everything is trained rather than we taught the model to do. And then in the future, maybe we can do meta-learning or reasoning leads to generalization, maybe make the model even more generalizable, because for the RL part, it's not as generalizable as pre-trained yet, because for RL, we have a lot of human-defined reward, where you have a lot of human inductive bias. I'm not saying humans are bad, but we want the model to learn. It's like your kid, right? You want to teach your kid how to learn rather than teaching your kid to learn a specific things, which is, teaching our kids how to learn is much more important than teaching a specific, knowledge. Then there's people call this young LeCun cake, right? And the majority of the compute were spent on supervised learning, and then the self-supervised learning, right? The icing is the supervised learning, and the cherry on top is RL. Basically, people are saying, in this regime, RL is a tiny amount of compute compared to the pre-train. But we believe that we need to change that. We believe more RL is required to build AGI and ASI, and to adapt to entirely new environments. Those environments not seen by human hand before. So I think that started. Let's go back to beta license again, because I read it several times. I want to quote it many times. So remember, there are two things that we discovered in the last 70 years that scale really well with compute. One is learning, right, which is pre-trained. One is search. We haven't applied search that much, yeah? And so that's why we want to start paradigm 2. Like OpenAI started this for pre-trained high computer RL. So 2014, the O series came out. It started the next paradigm of scaling. So we want to scale the test time compute and RL compute. If you look at also 2025, there is an open source version of this from DeepSeek. And if you look at the performance on Amy, anyone took Amy in this room? Only one, two? Come on, more people take Amy. Oh, three. Cool. So this is the Amy score when you give more compute in the train time. You can see from like 40 points to 80% percentile, right? And then for the test time can be similarly from 20 to like 85 or 90. So giving the model more time to sync can significantly improve the Amy performance, which is pretty challenging task. It's not that trivial. This is a new paradigm. We call that high computer RL. So basically, a lot of capabilities are really enhanced with reinforcement learning. But the caveat for there is on the public, the papers published, a lot of them only work well with verifiable rewards, meaning it's a math problem or it's a coding problem. You know that's correct or not right in the end. And what we need to really do is to expand what is verifiable. And there's a recent paper from David Silver and Rich Sutton called Welcome to Viral Experience. I think almost exactly, illustrating the importance of this. And so the core idea, I think, behind that paper is high quality human data is limited. Like even though we have maybe thousands of years of civilization, right? But the actual data we accumulate is not that much. We already consume most of the intelligence text. The idea is, how do we generate more data? But then you ask yourself a question, where does human data coming from? Where are the human intelligence coming from? The human data coming from human brain thinking and getting reward or feedback from the real environment, which is the Earth, right? And then, given that we know compute is going to get cheaper and cheaper, we want to generate new knowledge and new data by using more compute from the computers rather than human brains, by letting the computer interacting with the environment and generating a lot of data. I think that's going to be faster than human generating data in the future. That's why I'm so bullish about AGI and ASI. The other thing is just an anecdote, why does training ourselves work, right? One thing that always puzzled me since the beginning of LLM is why we spend the equal amount of compute on every token. It doesn't make sense. Like in your training corpus, right? There are tokens from the random internet, the chit chat on Reddit, right? And there are also really intelligent conversation between two mathematicians, for example, right? And not every token are created equal. And so we should not spend the same amount of compute in training and testing time for those tokens. And that's where chain of thought is coming from, right? In chain of thought, you can actually spend arbitrarily long tokens for a really hard problem. And that gives you this adaptive, compute. So the thing we want to do is basically same flops per intelligence rather than, same flops per token. This is my personal journey. I don't summarize it. Initially, I'm very spaghetic about the AGI because there are a lot of fat. That's non-convex optimization. We know that can lead to very bad things, right? And this over-parameterization from theoretical perspective before in traditional statistics, that's a bad thing. And the other thing is that prediction leads to understanding. And we don't know, right? But there's a lot of good theories believing that that's true. And RL can also be most seeking. There are a lot of people worried about that. And the biggest one actually for me to overcome is I always believe human brains are special and human intelligence unique. And before, for example, all the things we talk about mathematically, they're trivial. They're basically tensor multiplications and the gradient descent. There's nothing fancy about that. So make you wonder, are we really that easy to replicate or to mimic, right? And I believe less and less so, like human brains are so special as I understand a little bit more. Like you can simulate the human brains in many ways. Why not, computers learn the same way as we do? And so those are, next page is why I'm more AGI peeled, right? One is perhaps, brain cells aren't uniquely special. It's just basically a result of evolution. And they are overly complicated, right? This is just a biological computer. There's nothing special compared to a, artificial silicon computer. And the other thing is maybe scale is the thing matters more fundamental rather than how complicated the structure is. And intelligence actually may not rise from the complicated structure we have or computations we have in the brain. The intelligence may rise from the data and the interaction we have from the environment. But maybe our brain, we talk about why those simple tensor or matrix multiplications can lead to intelligence. I don't think our brain is doing something way harder than that or way complicated than that. We're not doing quantum computing within our brain in any way, right? And okay, come back to Rich Sutton, right? Similar, Turing had the same idea 75 years ago. Rich basically says, I know human mind is very complicated, and but we want to make sure we can simulate an infant brain and give that a course of education to make that really intelligent. And this agrees with Turing. And I think also, if you ever feel confused, I always go back to Rich Sutton and Turing and read their old papers. And those are the people who are actually ahead of their time for like a few decades. It's amazing. And the other thing making me AGI peeled over the last 2-3 years is you constantly observe impossibilities become realities. Every couple of months, something you thought impossible become possible. And then you start doubting, all the things you thought impossible, they're just BS, right? Just ignore them. And so even though there are a lot of open problems and lots of reason to be, but there are also a lot of reason to be optimistic. We will talk about the open problem in the next part of the talk. I'm going to check how I'm doing on time. Good. So let's talk about open problems. And I want to make a few definitions to keep the discussion grounded a little bit, because everyone has different definition of the AGI and the ASI and so on. So AGI, what I mean is a system that matches human level skill across virtually every domain. Like, it's a human level breadth. It's basically the word that matters is generalizable. It's not a special thing that built for Go or for a video game. And ASI is a system that surpasses the best human in every domain. And task specific superintelligence is a system that surpasses human only in specific domains. For example, AlphaGo, OpenAI 5, those surpasses human champion in a certain domain, right? We call that a task-specific superintelligence. So what are the open problems? And a lot of people say on the internet, say scaling law failed. And maybe it's a different perspective. I don't think scaling law failed. The data failed. Remember my personal perspective is scaling law is the reflection of the data structure. So it can never fail. It's just a law, right? It's a mapping. And what really failed is actually the data. And so what do I mean by that is maybe to fundamentally improve the capabilities, what we need to fundamentally improve is we need more or better or higher intelligence data, and so that the model can learn it through the scaling law. And so learning to me is fundamentally data bounded. If you have infinite data in every domain, we already solved the AGI, given infinite compute, which, here's my way of thinking, right? Infinite compute gonna be here sooner or later. I don't worry about that. And but the thing that really bottleneck us is the data. And then people ask, right? Then we talk about we can actually convert compute into data, because human data are converted from human compute, right? From our brain. But why not convert the silicon compute to data? But there are a few caveats that we didn't solve yet. One is right now it's only limited to domains where the results are verifiable. And they don't, current IL may or may not effectively generate results outside the support of the previous policies. That's exploration. And the other thing is, you remember in AlphaGo, we did the Monte Carlo tree search, and you do the random exploration, and which can lead to win or lose the game. You cannot do that in language models. The reason is language model is just many order magnitude larger. The space is many order magnitude larger than Go even. So a random generation of tokens can never lead to anything. That's a strong word, because when we have infinite compute, things change, right? You have people say you have a cat, giving a typing machine, if you type Shakespeare at some point, but that's just going to be a super long time, right? By random luck. So that's one dimension. We want to improve the data we have. The other direction is actually to improve the data efficiency of learning. If the fundamental bound is data, we can either get more data or we can make our algorithm more data efficient. So that's we can talk about both of them. Better one is generating more and better data faster. We talked about this before. And if you think about how much data we accumulated, we have been accumulating printing press data for about 1,000 years, right? And which in the beginning was very minimal. And then we have been collecting detailed data for the last 2 years or so. And so from the whole chain of where the human data coming from is one, the human first give a task, right? Inspired by the environment. It can be solving polynomial equations. I don't know anyone know the history of solving polynomial equations. People were gambling around that and try to get rich by solving more polynomial equations, right? And I mean, the initial task we human gave is to survive. And that's the meta learning. And then the current generation of humans learn the existing knowledge. And the third step is think about the problem for a long time. Maybe some genius came up like Gauss, Galois, and those people invent new knowledges, right? And then you get feedback by interacting with the environment, the peer-reviewed whatever. And then you distill this new knowledge into, this new finding into knowledge. You write a textbook on calculus, and then later I'll write a paper on calculus, and then later generation you'll learn that. And then you iterate. That's how humans generate our data, generate our knowledge over the past thousands of years, right? And which aspect, we can significantly accelerate by using AI or by using silicon compute. And so about tasks, there are already a lot of open problems. For example, there are a lot of open conjectures in math, like Riemann hypothesis and so on. But maybe there are too sparse still. You don't have a good clear theorem, right? And for learning, so that's stage one. For learning, I think model can learn very fast with weight or in context. So we will talk about later how to make it even faster or data efficient. And for thinking and search, models can think very fast. And but the key question is, can model generate new ideas? It doesn't matter how fast you think, if there's no exploration, right? And then we ask ourselves, how does human discover new knowledges? Like, I think the fundamental driving force is curiosity, right? We are curious, so we always explore new things. And so we want to really teach the model to be curious. And there are different beliefs. My personal belief is maybe interpolation and exploration is enough. Like the model knows so much, and that they can just interpolate and extrapolate some knowledge, and that's enough exploration to advance intelligence. And I think maybe just 1 more minute on that. Do I have time? I do. So the last, the universalist for math is kind of Poincaré, right? Which is 120 years ago, almost 130 years ago. And so the model now actually can know all the subjects of math. So it's a universalist, right? So it can maybe generate a lot of new knowledge or new ideas in that way. And the other most important thing for a human to get new knowledge is interacting with the environment. And this can be very efficient for computers if there is a perfect simulator. For example, for board games, for Go, you can just simulate it on the computer. So you can get infinite data by using compute. And this is a fundamental blocker if you cannot simulate. Or the sim to real is really, the gap is really big, right? People are building this called word models for video, or for the whole world, for physics and so on, which is really hard still. And so that's why the embodied AI is harder. You don't have a perfect simulator of the physical world we live in. And so I'm still optimistic though, because if we can build a model that can reduce the search space like AlphaFold, so we can build a positive flywheel. You have more efficient search, and then you can generate more data, and then you have even more efficient search and so on, right? So that positive flywheel can lead us to super intelligence. And distillation model can do this very efficiently already when you have a new knowledge. Yeah? Yes. It's more older. So it seems like a fundamental how humans drive knowledge. They're given way right off. Whereas So I want to repeat the question. The gist of the question is, when humans discover new math, a lot of them are serendipity, right? There's no particular goal. First, I don't agree with that premises. A lot of the pure mathematicians, they still have a goal to solve. A lot of the math we invented in the process of solving a conjecture, right? But there are definitely a lot of serendipity into those. I have a perfect answer for that in a few slides. Okay. The other thing is, open question is embodiment necessary for AGI? It may or may not be, depending how you define it. If you are defining AGI to be the virtually, economically valuable task, maybe not. And but the thing is, humans can be the part of can behave like the embodiment for AI for now, right? For example, if the AI want to do this physics experiment, they don't have and currently AI don't have the embodiment to do that, but maybe humans can do the experiment for the AI and give the result to AI. And so that can also form this positive feedback loop. And we do want to avoid the future that the AI will, we just become the embodiment of AI, which is not a good future to live in, if you. The other current fad is, can RL generate new ideas? That's a recent paper saying, like, can reinforcement learning really incentivize reasoning capability beyond the base model? The base model is a pre-trained model, right? So they did this analysis. So this is a number of samples, and the Y is the pass at K. Basically, you pass at 1 meaning you do one rollout and that rollout is correct, right? Pass at 1 million means you do a million rollout and one of them is correct. And what they found out is, after we do RL, the pass at 1 increased significantly, right? But pass at 1 million is the same. That basically means if you generate 1 million possible results, one of them is correct even from the base model. So the RL model didn't generate anything new. I don't agree with that finding because this is on a particular few open source models and so on. I do believe RL will and can generate new ideas, and we will see that in time will tell. The other key thing is exploration. This leads to the question: can we do more effective exploration in RL? Like we talk about humans has curiosity, and that leads to exploration, and we believe exploration is definitely needed. And how to do that is open problem. And this goes back to interpretation and exploration, and maybe that's enough. And I'm personally very optimistic because if you look at on the human, how human advance science and technology, right? How much of them is purely, genius idea out of nothing? It's a very tiny amount, right? Most of our work in science is based on interpolation or exploration of the previous works, right? The model can do that if incredibly well compared to humans. I think that's maybe just enough. I will save the question in the end, so we're running out of time. So there's a really encouraging evidence from Alpha Evolve to validate the idea. If you haven't, please read that paper. It's a fascinating paper, just came out like a month ago. So they actually demonstrated the power of in-context learning and guided exploration. So what they did is, remember, I think when I was undergrad, was learning how to do the matrix multiplication very efficiently, right? And the state-of-art algorithm was 1969. Wait, how many years ago? A lot of years ago, 50 years ago. Yeah, it's 50 years ago. It's crazy, right? And then you use AI to improve upon that. Basically, this is the state of art. Can you improve upon that? And step by step, they actually discovered a better algorithm than that. And this is very inspiring. Basically, AI can solve the problem we didn't know how to solve for like 50 years in some sense, right? And out of the 50 open problem, I think 20% of them, they improve the state of art, especially for this, NP hard or comparatorical problems. AI are much, much better. And I really believe, I studied pure math. And the reason for that is in the freshman year of college, I learned Galois theory. And I attended a seminar by Professor Huang in my university, and I just got fascinated by Galois theory. It's just so beautiful and amazing, and that leads me to pure math. And then my dream was, I want to solve a conjecture, something like a Riemann hypothesis, right? And a couple of years in graduate school, I realized I'm not suited for that. I couldn't do that. And so I gave up. And now my new dream is we can build an AI to solve Riemann hypothesis. And I'm much more confident about that than myself solving Riemann hypothesis. The bet number two is we want to vastly improve the data efficiency in learning, right? So if you think about the current AI now, the data efficiency is still very bad compared to human. Like for a well-educated human, if you teach the person a new board game, it probably require like several minutes or maybe 1,000 tokens to learn, right? To play like a game pretty well. But the current SOTA model couldn't do that. It's required maybe still 10x, 100x more tokens to teach a model something really well. And but make you think why that's the case, right? One thing, this is just personal thinking and discussion with some friends, right? Humans do not learn by predicting next tokens, do we? We do not. We do sometimes try to predict what you're going to do, what your next move is, but we do not predict exactly what your token is. And the reason for that is, that distinction is really important because predicting a token, meaning there are a lot of random structure in the token that the model trying to predict. So basically, the model is wasting a lot of compute and parameter to predict something random. As humans, we predict on a much higher level, at more abstract level. So that way, we know the essence of the problem rather than trying to predict the structure of the tokens. But because think about the idea, there are a million different ways to say the same idea. But if you're predicting the next tokens, you're trying to capture these random structures in there. But I have no idea how to solve this, like what's the next paradigm is. So yeah, this is I think the open question, how do we vastly improve the data efficiency? So if we can solve that, I think that could be the next paradigm for AI. The other thing is let's make the open problem is like misreasoning much more generalizable. Did I answer a question through this slide? Or should I? So let's go back to that. Your question was, mathematicians discover things a lot of time by serendipity, right? But models are not. I think this goes back to this slide, the Poincare, right? And I agree that some of the discoveries are by chance, right? Not by any utility or anything. If you go back to, I think, sorry, this one, from Sir Isaac Newton. I don't know what I may seem to the world, but to myself, I seem to have been only like a boy playing on the seashore and diverting myself now and then finding a smoother pebble or a prettier shell than the ordinary. And well, the greatest ocean, the truth lay out undiscovered before me, right? This is a very poetic saying. I really love that quote. And to your point, meaning some of the science and technology were discovered by serendipity, right? But AI gonna improve. It's basically a search problem. There are a vast space of science we need to search, and then we get a pebble or we get a shelf, right? But the good thing about AI is AI gonna reduce that search space so much, serendipity become common things. Right. So like, but I'm sure actually sort of chunks going up through a bunch of structures, and then use that repository. I think that's a really good point. We can talk about that after the talk a little bit more. I'm really optimistic, and I also see progress in the directions like that. And I don't believe anything special about human serendipity and compared to machine serendipity. Let's continue. The other open question is what's the next scaling paradigm, right? We talked about some of that. If you look at the paradigm 1, paradigm 2, we scaled the depth of the layers, and we scale the test on compute and RL. Maybe you want to scale the number of tools, self-play, context, and memory. The model still don't have infinite memory yet, which is really important, right? Because for a really good friend, you share a common memory that is almost infinite. And lifelong learning, are really, really important. I'm running low on time, so I'm going to be a little bit faster. And the other is safety, right? There are three kinds of safety. One is model may generate unsafe content. This is very similar to traditional trust and safety work. And the second one is maybe bad actors going to leverage the model to do bad things, right? We want to prevent that from happening. The third one is more serious or exponential, meaning the model itself becomes bad and misalignment. And there are a lot of research going into this. I think that's a really, really important problem we're tackling. And the third part of the talk, I want to, dream a little bit and see onto the future what I envision that the future can be. And some of them maybe in the near future, some of them maybe 5-10 years down the road, maybe more than 10 years, and maybe we'll see. So one quote I really like from Sam is, he always say the days are long, because everyone felt that, right? I had a long day sometimes, but the decades are short. And I also feel that I can't remember, I graduated more than 10 years ago. It's scary in many ways. And most people, because our human intuition, gonna overestimate the short-term impact of AI, or the short-term development of AI. But I think one of the reasons I want to give this talk is I think most people also underestimate the medium to long-term impact of AI. It's gonna fundamentally change everything. And so let's see what's the future gonna like. I have a hypothesis. When we have a generalizable human prayer, we have unbounded computing RL, and we have a good environment, that equals to super intelligence. And if you look at how human learn, that's exactly how human evolved, right? And we think the model can evolve even faster than that. So let's see. The first area is, I think agent going to be everywhere, and you will see much more reliable and capable agent in the next year or so, and it become a reality. And I think to a large extent, it's just basically an execution problem, and there's not a lot of research open problem to make agent work. AI for science, something we went to the slides before, but something I'm really, really excited about. And if you think about science is a search problem, right? It's a massive search space. And once we have enough data to bootstrap a model, then you can make the search much, much more trackable. And I think on most subjects in science, we're actually in that environment, or in that stage. We accumulate enough human data. Let's use AI to make the search more trackable. And if I really hope that, move 37 of the AlphaGo moment, do people know about this? Or should I explain a little bit? Yeah, good. And there's a quote from Max, who is, I think, the chief scientist from the isomorphic lab, saying, I really agree with that, by the way. Doing drug design without AI is like doing science without math. I think, AI become the new math for science in the next decade or so. So if you're not using AI in your research, please consider doing that. I think every university should have a huge, either develop their own model or own clusters or use the cloud. And it's going to be, accelerate science discovery a lot. And I'm really fascinated by AlphaFold and a lot of material science and AlphaEvolve we talk about, right? And our friends working in the AlphaFold, areas, they're telling me a lot of the drugs are already actually in clinical trial. I always, thought that's kind of in the far future, but over the last year, it's just progressed so much. One particular thing I think they're in clinical trial is how to neutralize the poison from snake bite. Those are really easy problems. You just need to cover a certain part of the protein. And then from the protein structure, you go to amino acid sequences, right? But the problem before is from a structure to an amino acid sequence, there are millions of possibilities. And this is a gigantic search space. You cannot do that in the wet lab because you don't have enough graduate students or enough. Sorry, but graduate students are really good. And but then AlphaFold have that, from the protein structure to the amino acid sequence, there's a high recall, low precision mapping, right? AlphaFold is the inverse of that. It's a high precision mapping. Basically, you map to the protein structure space and compare to the protein structure that you want. And then you can narrow that down to maybe 100 or 1,000 amino acid sequence. In that way, you have enough graduate students to do the experiment. And so that's how those drugs go to clinical trials. So again, I think this is one more demonstration is AI can reduce the scientific search space a lot. So if you're doing any search in your discovery, use AI, math, physics, biology, chemistry, everywhere. This is the protein structure if you're interested. Let's go. And I also have a conjecture on AI for science. I really hope in the future that we don't, in addition to use graduate students, we have a lot of machines and robots in the lab that can automate a lot of the experiment, and then you have a really fast feedback loop. So basically the model comes up with a hypothesis. Oh, those are the amino acids you need to do, right? And then the machines just do it, and then come back and tell the AI, oh, this works, that doesn't, and the AI evolves, keep continuing training on that. And that feedback loop gonna be super, super valuable. And the other thing is, what I hope is, AlphaFold is a specialized model, right? What I hope is similar to from AlphaGo to LLMs. What if we can develop a generalizable model that for all the subjects, like similar to LLMs, rather than building a specialized model in science? And I think enterprise R&D gonna be fundamentally changed by AI. There are two things. One is AI can fundamentally boost the R&D productivity, for example, the coding agent. The other thing I'm even more excited about is maybe AI will lift the ceiling for a lot of R&D frontiers, similar to how AI gonna accelerate science. AI for education is something I'm super passionate about as well. And if you look at the society, I think one fundamental thing that people have access to different quality of education, and that leads to further divide of the society, or in a lot of ways. And there are two things AI can help. One is actually lower the barrier. AI can make advanced topics more accessible, and because it's synthetic data, right? If you look at a random internet article about a subject, you may get intimidated. It's not friendly, put in a way that's friendly for you to read, but AI can lower that barrier a lot, right? And the other thing is AI can become your personal tutor, can be personalized. And there are studies showing if you have a personal tutor and your learning efficiency like double or quadruple, right? In a lot of cases. The other thing is raise the ceiling, and what we call 10x learners. LLMs I do this all the time now over the weekend, is I just run, a dozen different deep research on different topics I'm interested in, and then you read the report, and you suddenly become not the expert, but you rather than become a total stranger to a field, you become the entry level thing, which is amazing. And the hypothesis we have is maybe in a few years, rather than spending 5 years on a PhD, maybe over 5 years, you're going to have 5 PhDs or 10 PhDs, and if you really want to learn. AI for healthcare, that's super, super critical as well. I think AI is already better than the healthcare provider most people have access to. And we have numerous examples how ChatGPT can save people's lives, and that are not fake, and they're really real cases across different domains. And the other thing I'm really excited about is if AI can have the holistic context of the patient's medical and health history, I think that can maybe, rather than cure diseases, they can actually predict or do a lot of more preventive healthcare in many ways. Embodied AI is something maybe a little bit further away, but once that's true, then it's gonna has tremendous impact to the society as well. It's not as mature because we don't even know how to efficiently tokenize actions. There are suggestions, but they're not super good yet. How to leverage existing massive amount of video data to enable generalization. The key thing about embedding AI is we do not have a lot of data. Like if you look at how LLM started, I did a Twitter post, I think on January 1st, about the following, and then it got really popular. I actually deleted that post. And the following is, at that moment, I felt over all the years we have been preparing for AI. Why I'm saying that? Like we invented printing press, right, to record our intelligence, and then we invented computers, and then we invented internet. All those things leading to accumulation of all the data we need to build AI, and all the compute capabilities we build lead to the capability we want to train AI, right? In some way, we have been preparing for this for like thousands. Human being has been preparing the moment for AGI for thousands of years. This is a little bit emotional, that's why I deleted it. But if you look at robotics, we do not have the internet equivalent of robotics. The only way maybe if everyone has a recorder from their eyes, or how things are in the real world happening, right? We do not have the amount of data for robotics to be super effective yet. But even we have that amount of data, we don't have good ways of a really sample efficient way to learn that yet. So that are the two open problems for robotics. I mean, a lot of the demos are really cool for robotics, but the demo to product gap is pretty high, in case you don't know. Here is my dream come true case. Like the universe, maybe one of the reasons we never discover aliens, there are many, right? One is maybe we communicate in different modalities, like we never discover each other, we live in different dimensions and so on. And the other reason is most of the universe are not inhabited by human, right? So we go out, it's really hard. But they're not true for the silicon intelligence. What if we build embodiment intelligence that can explore the universe for us? And I think that's going to be super cool in the future. That's the end of my talk. And thanks for your attention. I'm happy to answer any questions you have. This is a code I got from, I think, Rich Sutton. And this is a PON. This applies to a lifelong agent in RL, and also applies to humans. Never stop learning.
Oh, hi.
Yeah.
Thank you for the great talk. I have two questions, I think. One is, what is the Moore's law for LLM, and where are we on the curve? Okay. That's part one. And the second is, I think I'm a skeptic of the AGI because what we are doing with all the neural networks and the matrix multiplication is, I think, a very narrow part of the human mind, which is just human reasoning. But human reasoning is a very narrow part of the human experience. I think we're hardly touched on the human experience is also consisted of emotions, which is very, very early in the process of that. And I think there is another piece which we're completely missing is what is the consciousness, self-consciousness. I think NYU, some people are studying that, but I think without any of that, we'll never get anywhere close to AGI or ASI. That's my.
So to answer the first question, I think the Moore's law can mean many things, right? One is Moore's law for LLM can be interpreted as the scaling law. And I think as we discussed, I think for scaling law is an intrinsic property of the data. We really want to make better data, higher quality, more data faster, right? And in terms of a lot of consciousness about AI and so on, I agree. And I don't have a really good definition of consciousness. There's one paper quoted by Rich Sutton. Again, I think Sutton just solved all the doubt I had. But he mentioned that maybe consciousness is coming from embodiment. Like we are conscious because we have a body. Like this is my feet, my arm, and this is my head, and so on, my heart. And I don't know if that's true or not because I don't really understand what's consciousness. It's kind of a little bit abstract to me. And but I agree, there are just definitely a lot of open problems. And but I'm optimistic.
We're going to take two more questions. Okay. Oh yeah, Luca. It's our department chair. I want to make sure we get to him.
Hey, thank you for a great talk. Two words that came up a lot in your talk, I think, are efficiency, often related to data efficiency, if I understood correctly,
yeah,
and scalability. And then at some point in the talk, you had a sentence about the human brain. And I don't know if it was provocative or not, but you said, after all, maybe it's not so special. My understanding is that the human brain does often, not always, a lot of amazing things while staying within 20 watts.
Yeah.
So my question to you is, how would you talk about scalability and efficiency if you consider also the energy aspect?
Yeah, I agree. I think human brains are just so much more efficient in terms of learning than the silicon computers right now. And I don't. But the two aspects of this, right? One is there are enough data in a lot of the subjects already, even though the current LLMs are not as data efficient as humans, they can learn really well. That's one thing. And the other thing is, I'm not super worried about the energy efficiency that much yet, is because I'm really confident we can generate infinite amount of energy and compute. And if anything holds, like human beings are really good at generating energies and compute over the long run. So we wouldn't be compute bounded in any way. I do agree on one thing is that I don't have really good thinking along is humans just learn so much more efficiently. Like we just see a tiny fraction of the data the machine sees, right? And to me, that's kind of the either the model architecture or the loss function. Like we talked about the next token prediction loss. That's not how human brain does. We have a higher level abstraction of learning things. That part is an open problem. I don't know how to address that. Anyone who address that gonna win the next Nobel Prize.
Oh, thank you, Shuchao. My name is Nick Gu. I'm a computational neuroscientist and a neuro AI researcher. Our question, I should have two, but I'll only ask one. So there was a paper published by Apple probably in the past few days saying that the reasoning for moderate complex tasks for these models actually break at a high complexity.
Yeah.
So I accidentally read a paper from 2010 where they were talking about human reasoning models, and it comes to mind that humans do not always use pure logical reasoning. I'm sure audience can think about last time you made a decision with purely logical reasoning. I'm curious to hear your perspective on specific AI developments in terms of the reasoning models and how it would be. Sorry, a bit nervous. How are you able to share about this?
So thanks for the question. First, you are the real expert. I'm just I know nothing about the brain, and but I didn't read that paper. I do see a lot of discussion on Twitter about that paper, and then there's a new paper coming out, a Cho paper called "Can Human Brain Really Reason?" Right, and so I think all depends on our definition of reasoning. It's just it's more about like do human reason. Like, does the human brain think that's called reasoning according to that paper definition as well? I think that's an open question. We don't know.
Yeah,
And
do
to
one
me,
more.
reasoning is the way that you plan and you backtrack all those common patterns humans do. I think currently the model can already do that pretty well. So I tend to not argue about more like abstract and hypothetical things, but more in terms of utility, they're actually mostly there in many ways.
Well, last question.
Hey, thank you so much for joining us. I have a pretty simple question. My name is Talha Khan. Do you believe there is a general algorithm for discovery and invention?
So there's a spectrum of discovery and invention, right? And there's interpolation, and there's random exploration, basically, right? And if you look at AlphaGo, the Monte Carlo tree search explored some randomness in there. And then because they can always have a win or lose situation, the randomness is okay. Then you can learn from the randomly good or bad things. And I don't know a really good algorithm. My belief is still maybe extrapolation is something in between, and that can take us already super far. The ceiling is already super high. And in terms of how human serendipity works, like we discover things randomly, that's hard to understand. I don't know that.
Thank you so much.
Thanks everybody for coming. So do keep us subscribe to our engineering Twitter accounts or like LinkedIn, so we have more better lectures in the next semester as well. Thanks again for coming. Bye.